Hello, welcome guys back. We are in this video today. We're going to be exploring the boundary condition from Maxwell equations, and in this video we're going to be diving to multiple topics about the boundary condition in electromagnetism. First of all, we're going to see the meaning and the mathematical forms of the electromagnetic boundary conditions. We're going to try to derive it. I'm not actually going to go and derive it from the Maxwell equations or derive the Maxwell equation itself. I'm just going to give you the equations of the parameters that like the electric field or the magnetic flux and what in relation to the boundary condition. And so we're going to talk about some application like fiber optics, cables, and how they are related to the magnetic or the boundary condition in electromagnetism. And we're going to talk about the guided and evanescent, which is the decaying of wavelength, that's or waves. That's what evanescent stands for in dielectric interfaces. So pretty loaded lecture, but we're gonna be like dissecting it to their basic forms and go over the boundary condition. So let me jump to the second slide. So why do we need boundary conditions? So just reading the first paragraph or the first chunk, it tells us that the boundary condition describes fields in space. So it doesn't like talk about stuff that actually like strictly inside the wires or the whatever like is transferring. It could be like, for example, the fiber optics or the light. So it's not strictly about what inside the cables or the wires. We're talking about stuff that's inside and surrounding it, like or in around it, pretty much in the space or the medium. But it's used to solve for a specific problem, like a wave guided or antenna. And in this case, because you have two interfaces, like in the antenna, you have the air and the like the antenna itself. These are two different interfaces, so we're gonna use the boundary conditions. These boundary conditions describe how fields behave at the interface between different materials. As we see, like the antenna, it could be like the medium, which is pretty much the air, and the antenna itself, or wave guided, or for example, capacitor, you have the dielectric, or you have also dielectric and the the capacitor itself, which is like the sheet, the copper sheet, or whatever made the sheet of the capacitor. And yeah, it's here like it could be also dielectric or conductors. So between the dielectric and the conductor itself. So physical interfaces where boundary conditions apply. So as you said, like the antenna, which is metal and air, dielectric, which is the fiber optics, which we're going to be explaining in this lecture, and dielectric conductor, which is the coaxial cables, which is like like you have like the core would be, for example, a conductor, and you have the dielectric, which is pretty much like a free space. Could be free space, could be any dielectric material. Then you have a conductor, and you keep going on and on, or you just kind of limit it to like the conductor dielectric or conductor dielectric conductor. And we have guides, which is the same thing as the concept of having a dielectric conductor materials. So in this table, we're gonna see that we have the field, the boundary condition equation derived from Maxwell, physical meaning, and special case. PEC stands for perfect electric conductor or surface current charge. So PEC stands, as I said, for perfect electric conductor. So in other words, like we ignore the resistance. There's no resistance in the conductor itself. So for electric field, which is already know what's electric field at this point. So it's the normal vector cross difference between the second and the first electric field at two different points equals 0. So when you see like anything means it's equal to 0 and you have subtraction, that means that both quantities are equal. and when both quantities are equal, that means they're constant. So tangential electric field is continuous, and tan here is stand for tangential, is equal to 0 at PEC surface. So you make sure that it's at the surface, because at the core you get different values, and the core usually the electric field is 0, so you don't really care about it there. So but like at this, oh, I lost the cursor, here we go. So at the tangential electric field is equal to 0, so it's constant at the surface of the conductor. The magnetic field intensity, we're not talking about the flux here, we're talking about the intensity or the strength of the magnetic field. Same format you're seeing here. You see n, the norm of the unit vector n, cross the difference between the strength of the magnetic field equals k, and k in this case is the surface current. So the tangential H jumps by surface current K. So like the first value and the second value are different by the value of the surface current. So your factor is, it's not a scaling factor. When you think about a scaling factor, it's just K. So like H1 plus K will give you H2. H2 plus K give you H3. So yeah, in a sense, it's a scaling factor. It's just addition, but like you can think about a scaling factor. So E tangential equals K at PEC surface. And just to make sure that we all of them are the PEC surface, because that's where the interface happens. We have between two different medium for the boundary condition. Electric displacement D, which is we think about it as, so this is like if you think about the electric displacement, or if you study electromagnetism, you don't talk about it too much. They talk about the first couple chapters, then they stop talking about the electric displacement, because it's usually strictly known for the dielectric or the capacitors. When I think about dielectric, I think about capacitors for some reason, but it could be for any dielectric quantity. But details how much free charges, not bound charges, free charges is producing the electric field. So if you think about it, electric displacement is what's pretty much creating the electric field. So these D and E are relatively connected to each other, but the difference here, if you take the same equation and replace the E with the D, you got the surface charge density, or the PS. Surface charge density, so it's the same thing as the magnetic intensity or strength. They jump by, instead of current density or surface current, they jump by surface charge density at PEC surface, and it separates the effect of, so D in a sense separate the effect of free charges from bound charges. So it makes Maxwell equation easier to understand or easier to solve, because it provides a path in solving when you have free charges instead of bound charges. Magnetic flux density, which is B. So now we're talking about magnetic flux, which is measured in Tesla or Weber per meter squared, and the magnetic field intensity, which is H, is measured in amperes per meter. So when you talk about the flux, it's always 0 in a closed medium, which means, lost the cursor again. So it means that we take the unit vector n times b2 minus b1 equals 0. So number b is continuous. So the flux is just, it flows through the PEC, which is the perfect electric conductor surface, but you got no penetration. So it doesn't goes through the walls of the wires. So these are the basic or the main parameters, if you think about them, or the main variables that govern the boundary condition equations or the boundary condition phenomenon. Now here you have one other table that summarizes what we just said. So ET, tangential electric field, that's Faraday's law, and the displacement, the electric displacement is Gauss's electric law of electricity or electric. and Gauss law of magnetism, which is the Bn normal. Yeah, we didn't talk about the normal and tangential. So if we move back a step, we can see that the D and the B, or sorry, yeah, D and B are normal. So we talk about the walls of the wires, and H and E are tangential. So we're talking about the flow of the wire. Like if we're talking about the tangential, we're talking about the flow of electricity or electrons through the wires. And B and D, with no penetration, but like it's kind of like we're talking about the walls. If there's any something happens like with the walls of the conductors, or the whoever is carrying, whatever material you're using carrying generating your electricity and magnetism. So intuition behind the boundary conditions, behind the condition, or the conditions themselves of the boundary condition. So tangential E field must be continuous to prevent infinite voltage drops across the infinitesimally thin boundary. So in other words, it tells you like if you have a voltage drop, if you have like a tangential electric field, if the electric field is changing and changing in the, especially in the reverse, like is dropping, you have a voltage drop, like a meaningful or like a noticeable voltage drop through the wire. Especially if you're doing like transmission lines, it's gonna drop like the power will not get to the home from the power station. And if you have the electric field growing up without bounds, that means like its electricity will, like the voltage will spikes up and will not like drops at all, and that's you get like infinite voltage, which is like cannot be achieved. Normal D field may change due to surface charge. So as you see, we show you there that the normal D field, which is electric displacement, is changed by the PS, which is surface charge density. And tangential H field can jump by surface current, but if a surface current exists, so no current, no magnetism, which is quite known. And normal B field is always continuous. There are no magnetic monopoles, so you don't get the monopoles type of magnetism inside the wires. Like you don't get like so you didn't get. We say monopoles, like one side has a lot of magnetism, the other side of the transmission line of the lines doesn't have any magnetism because it drops. So you don't get that. So you just get, and the reverse, right? Like if it's growing, so the side point will be like the minimum, and the will be the maximum. So you don't get this monopoles. You have like you get like these like the magnet characteristics of the wire. So so it won't be like what you have North Pole and South Pole. This we're talking about the monopoles. Like it's just it's consistent. So it's just like there are no magnetic monopoles and it's always continuous. Now we're talking about the fiber optics cables. What's a fiber optic cable? So everyone knows the fiber optic cable at this point, because we're like in the 21st century, and internet is widely used, especially in 2025. And a fiber optic cable is made of a core, which is higher refractive index, and a cladding, which is lower refractive index. So why we have different two refractive index? That's it's designed this way to trap the light inside the core, and you don't have leakage of light. So if you leak the light, you get like weak signal, discrete signals, not continuous signals. So you're losing information pretty much when you have the point where you start leaking of the light. So you need the light to be trapped in the core, which has the high refractive index, to stay confined inside the core, and you get the max of the signal. Max of the signal, I mean like as much signal as it can be. Okay, so light enters the core and is confined due to the total internal reflection. So that's why we have a refractive index of the core higher than the cladding. So that's confine the light inside the internal core by the total internal reflection. So that's pretty much how we design the core, the fiber optic cables. So now we know how the principle of it, but like what causes that is the boundary conditions. So at the core cladding interface, the tangential component of the E and the H. Now we're bringing back to the four parameters we just talked about. So the electric fields and the H and the magnetic intensity. Remember, magnetic intensity jumps by surface current. E is constant across the boundary. Must match across the boundary. So when they say they must match across the boundary, means that E must be consistent and magnetic field must jumps by the surface current. These boundary conditions lead to the creation of guided nodes in the core of the evanescent fields in the cladding. So what does that translate to? So guided modes mean in the core and evanescent field in the cladding. So guided modes may have a propagation of waves inside the core. So they go in sinusoidal waves. So they go like a sine wave or cosine wave, depends like how the propagation starts inside the core and keep going. And the evanescent field in the cladding, so means they're decaying outside, so you get confined the whole signal inside the cladding. Inside the core. Guided based evanescent waves, here we go. So in the core, field propagate normally. This is a guided mode or node. Did I put node in the first one? Modes. Oh, they're all modes. There's no nodes. Sorry. In the cladding, fields decay exponential. This is the evanescent wave. So as I said, evanescent wave decay exponentially. So it means like they decay very fast. Satisfying the boundary condition while confining the wave inside the core. So you don't get like interfere or interference in the signal itself. So if it's guided in the cladding as well, you get like interference between the two waves, and you get like some like spill of from the cladding into the core, and you get like these like mixed waves, and it could be destructive. So, but like when it's like in the cladding, if it's evanescent, that means there's no wave propagation outside the core. Why is this important? Without proper matching, light would leak into the cladding and be lost. So core must be bigger than cladding, the refractive index. Fiber optics rely entirely on the boundary condition to trap and guide light with low loss over long distances. Because remember, like our goal is to propagate, not just like to stop, or like get some interference, either loss or addition. We want a clean signal that propagates over long distances inside the core. So in summary, boundary conditions are essential in solving Maxwell equations because they describe how electromagnetic field behaves at interfaces between different media, a surface of conductor, or between dielectrics. The tangential component affects how charges and currents move along the surface. So the tangential, we talk about like how things move through the conductor or along the surface. Normal component affects how the fields penetrate or are blocked by the material. So you could get so you still gotta get penetration. Depends how the match or mismatch be between the two medium, or it could be totally blocked and you get no penetration at all. It could be like in between. So it depends. That's the normal. So we're having along the walls of the surface. Along the walls of the surface, and this along the surface. So just make sure like you distinguish what tangential is and what normal is. So normal is talking about the walls of the conductor and of the conductor's surface, and tangential we're talking about the along the surface of the conductor. So that will be it. Thank you so much, and we'll see you in our next videos.